Okay, we're going to continue on here. We're talking chapter 19, and we talked about transition metals, and we talked mainly about sort of some trends with transition metals and some of the important things, including electron configuration. And really, the reason for this is sort of the rest of the chapter deals with coordination compounds. And typically speaking, coordination compounds are made up of two things. They're made up of a counter ion and a complex ion. And within the complex ion, typically it is a transition metal that is present. Um, so typically you have some type of transition metal that obviously is positively charged and sort of electron deficient because it is positively charged. And it usually is attached to a number of ligands, um, which are essentially Lewis bases. And as we talked about last time, we essentially think of sort of this arrangement as a very much a sort of Lewis acid base type of situation happening. A reminder that the ligands are the Lewis bases, and those are the guys that will donate basically a pair of electrons to our metal, which is obviously, again, electron deficient as it has a positive charge. The metal will really be sort of acting as a Lewis acid in this case and sort of accepting those electrons. Now, as we also talked about, you can think of coordination compounds as really like an ionic compound. And what that means is there really is sort of a positive guy and a negative guy. And much like most ionic compounds, that is the order at which it should be written, both in the formula and also the name. It should always be the positive guy first, then the negative guy. And with that being said, that means that you really could have a counter ion that is positive, and you can have a complex ion that is negative, or really vice versa. It can really be either way. You could have the counter ion actually being negative and the complex ion being positive. So it is possible, thank you. It is possible to basically have either one of those being positive or negative. Um, the counter ion, again, you could think of as very much like an ionic compound, really just there to sort of balance out the charge. So the overall coordination compounds typically are neutral, so they have kind of a no charge. The complex ion, obviously, as we just talked about there, can either be positive or negative. And as we'll see when we start talking a little bit here about naming, um, it does depend on sort of where it's at as to uh, which one will be positive or negative. And it also affects, as we will see, the naming of complex ions and such, depending on whether or not the complex ion part of it is positive or negative. So I think that's sort of where we got into here, I think. So we'll just pick back up here again. So a coordination compound, as I just mentioned, again, is a complex ion with a counter ion. And in this case, again, we have a number of ligands, and things that make really good ligands or Lewis bases are things that are polar and have non-bonding electrons on some electronegative type atoms, like our nitrogen there has the ability to attach through the nitrogen. Our chloride, which obviously is negatively charged, which means it's got some electrons to give, also able to bind in there. Water is also a very good sort of Lewis base, as it's able to bind in through the non-bonding electrons there on the oxygen. Um, so when we would look, for example, at something like a charge on this, we would look at the ligands in terms of the charges of these guys. And these guys actually do not have any charges. These guys would have its normal -1 type charges. So again, it depends on sort of what the charge here is on the cobalt. Let's just say, for example, it was +4. In this particular case, overall, this guy would have a +2 charge, as those are the only things with charges that would be in this particular complex ion. And we will talk about how to properly name this guy as we continue on. Now, when we talk about ligands and how many ligands are actually attached to a complex ion or a metal ion, the number of donor atoms are atoms that are directly attached to the metal in the complex ion will give you what is referred to as a coordination number. So the coordination number is how many of the atoms are directly attached to the actual metal in the middle. Now, when we look at something like water, it will attach to the metal here through the oxygen, and the NH3 would attach through the nitrogen here to the metal. So if we had just these two, for example, ligands attached to this metal, the coordination number here would be 2 in this case. Again, the nitrogen attaching, the oxygen attaching directly to the metal in this particular case. Now, not all ligands are sort of the same. They do not all attach sort of a one-for-one sort of situation. There are certain ligands that can attach in multiple places per molecule. So if we look down here, ethylendyl is a very common one. And this guy is also abbreviated with an EN. And you will actually see that EN abbreviation both in formulas and actual names as well. So people use that sort of abbreviation a lot. It looks something like this. Again, a little bit of this. And here, this is basically EN here. And again, if it had a metal through both of those nitrogens in that one molecule, it will both be able to bind to the metal. So if you had two of these guys, for example, this guy would also be able to attach to the metal through both of these things. So in this particular case, the coordination number actually would be 4 in this case, as we have basically 4 attachment points to the metal. Now, if you looked at the formula for something like this, it may have like the metal and En2. So it's very important to remember that not necessarily will it always be sort of the subscript in the formula, especially if those ligands are not monodentate. If they are monodentate, then it'll be equal to the subscript. But if they are not, then you do have to sort of adjust it. As you can see here, you do get a 2-for-1 sort of situation. Probably the other most common bidentate one is oxalate, which is C2O42 minus. And oxalate looks something like this. And oxalate can bind through each of the single bonded oxygens. And again, you get sort of a 2-for-1 situation on this as well. So again, if you had 2 of these guys, you would get, again, 1, 2, 3, 4 attachments here, and the coordination number would be 4. So again, those two are probably the most common sort of bidentate ones that you come across. It does affect the coordination number. It is how many atoms, again, that are directly attached to it. Another one can, for example, bind in many places. They're sometimes referred to as being polydentate, which means they can bind in multiple places to the metal. EDTA is an example of that. EDTA is a compound that does a really great job of basically surrounding a metal. It can bind in like 6 places per molecule. So if you have one molecule of EDTA, it's going to basically grab onto that metal in 6 different locations, and it's going to really tie up that metal really, really well. So coordination number, not always, again, like I said, sort of the subscript that you see in the formula. Sometimes it is if it's monodentate, but if it's some type of bidentate, polydentate, you do have to sort of adjust that. Any questions on that there? So how many sort of ligands do we typically get? It is sort of based on charge. Generally, if we have sort of a +1 charge, you're probably gonna get somewhere between 2 to 4 ligands going to basically attach in there. If you get up to like a +2 sort of charge, you're probably looking more of 4 to 6 in terms of the coordination number, and definitely a +3 charge would lean more towards a 6 of them, except for gold, which will kind of roll typically with 4. So the larger deposit charge, the more electron deficient it is, right? Which means it's going to be able to accommodate more electrons coming in because it's very electron deficient. So it's going to be able to accept more ligands than, say, something at this end, which has just a +1 charge, not as electron deficient. Maybe can't accept as many ligands coming in. So there again is our ethyl endyl diamine, and this is EDTA. And as you can see here in the EDTA molecule, it's basically able to attach in 1 spot there, 2 spots, 3 spots, 4 spots, 5 spots, and 6 spots. So that is 1 molecule of EDTA. And it's able to basically grab up the metal in 6 different spots. Makes it a really good, what's sometimes referred to as a chelating agent, because it's basically able to surround that metal. Several of these ethyl endyl diamines, these EN guys, also really good job here. If we were to look at the coordination number of this guy, this would be basically a metal with 3 of these guys attached. And because there's 3 attached, they're bidentate 1, 2, 3, 4, 5, 6. Coordination number here again would be 6 in this case, because it's able to really bind in 2 places per atom. Any questions on that there? So here's a table, and again, here's our ethyl endyl diamine tetraacetic acid, which is EDTA on the bottom. This is water, cyanide, ammonia, nitrite, hydroxide. All the halogens are good Lewis bases and ligands, where the D should be, I guess. And there's our oxalate and our ethyl endyl diamine. This is actually diene, which actually has 3 nitrogens. And again, at each of those nitrogens has the ability to bind into a metal. So if you had a metal there, you would get basically a 3-for-1 sort of binding situation happening in that guy. In terms of his coordination number, it would be basically every one would give you 3, basically, in that case. You could also see here again our EDTA at the negative oxygens, basically. Guys with the negative formal charges, they're able to attach, and also at the 2 nitrogens, they're able to do that as well. So why don't you take a second here, and we're looking for the oxidation number of the transition metal and the complex ion. And just to tell you, typically when you look at a formula for a coordination compound, the one in the bracket is the complex ion. So that is typically the complex ion. So what is the oxidation state of the metal that's in the complex ion there? Take a moment and see what you come up with here. Okay, so let's take a look. So we're gonna start here with our K, bless you, AuOH4. So again, typically speaking here, the guy in the blank screen, the guy in the bracket here is going to be our complex ion. That means that in this case here, this is going to be our counter ion. So if we go to sort of the sign oxidation states here, we have OH, which is hydroxide in the parentheses. That's -1. There's 4 of them. Gives you a -4 happening there. On the outside with our counter ion, that's potassium. That's group 1, which means it's a +1. That means in this particular case, the oxidation state here of our gold is +3 here to get us to 0. Any questions on that? Looking at our other one here, we have CrNH36, a little NO33 happening. Once again, looking at this, it's actually going to be up front here is going to be our complex ion. And that here would be our counter ion in this particular case. So starting with ammonia, ammonia has no charge, right? It's neutral, so not +1. It's not ammonium. That's NH3, which is ammonia. NO3 is nitrate, and that's -1, and there's 3 of them, which gives you a -3. So it balances out here. The chromium is rolling with a +3 charge in this case. First off, any questions on assigning those oxidation states there? Now, when we look at just the complex ion part here, and we just pull out the complex ion parts, what is the charge on the complex ion in this case? The overall charge on complex ion is? It is -1, as this is -1, and that's -4, as we determined that was +3. That means overall here, our complex ion is going to be -1. It is a negative complex ion, and that is why when we look over here to our counter ion, we just need 1 potassium at +1 and -1. Gives us no charge when we put it together. So again, that counter ion there just to balance out the charge like a normal sort of ionic compound. Any questions on that one there? Now, if we look at the guy on the right here and we look at just the complex ion part, as we saw above there, our ammonia is 0, our chromium is +3, which means this complex ion here actually has a +3 charge and is positive in this case. And that is why when we look at the counter ion for the second one, we need not just 1 nitrate, not 2 nitrates, but we need 3 nitrates to give us a -3 overall to balance out the +3 overall here. So again, we put it together like a normal ionic compound to equal 0 in the simplest way possible to do so. And again, as we can see here in the first case, complex ion is negative. Counter is positive. And vice versa over here, we got a positive complex ion. And a negative counter ion here. As I also mentioned before, when we write formulas for complex ion or coordination compounds, it is always the positive guy followed by the negative. So just where those guys are arranged in the real formula, we already know that that guy is going to be positive. Overall, the complex ion is going to be negative. Just like here, the complex ion came first versus the counter ion. So we know the complex ion is going to be positive and our counter ion will be negative again. That's how it's written in the coordination compound formula, positive then negative. Any questions on any of that there? All right, then let's talk a little bit about how we go about naming these guys. And there's a bunch of sort of interesting rules that we follow when we go to name these guys. So first off, as I just pretty much mentioned, we are rolling with the positive guy first, so cation first, and anion. And again, as I mentioned, that goes for formula and name is how that should always sort of pan out. When you're naming the complex ion part, so again, remember, in a coordination compound, there's the complex ion part, there's the counter ion part. So whichever part that is, either positive complex ion or negative complex ion, when you're naming the complex ion part of it, what we do is we put the ligands that are attached in alphabetical order, and the metal name should always come at the end of the complex ion part. That doesn't necessarily mean it'll be the end part of the name. It could be the front part of the name, but the end part of the complex ion part should always have the metal at the end. Ligands do come in alphabetical order regardless of prefixes. So we may use some prefixes if we have more than one ligand of the same ligand within the compound. So we do go alphabetical order regardless of prefixes. If we have an anionic ligand, so something that is negative, they typically end with the letter O. Neutral ones are usually called by the name of the molecule. There are some exceptions, or a number of exceptions, like water is called aqua or aqua. CO is carbonyl. NH3 is amine. As I mentioned before, if you do end up with multiple of the same ligand within the complex ion or the coordination compound, we do use prefixes to indicate how many we have. Di for 2, tri for 3, tetra for 4, and penta for 5, hexa for 6. Now, if the ligand itself actually already contains one of those prefixes, like di or something like that, then we actually use different prefixes if there's multiple ones. Bis, tris, tetrakis, bis for 2, tris for 3, and tetrakis for 4. So what do I mean by that? If we go back to the one that we saw here, right there, this guy right here is ethyl endyl diamine, and within the actual name of this guy, there is the di part. So because the name already has a prefix in it, if you had more than one of these guys, you would use something, say, like bis if you had 2 of them, or tris if you had 3 of them, or whatever it may be. I will say that some people, it's very common, although it really doesn't necessarily have maybe a prefix that you normally would associate with it in it. People also do the same thing for oxalate, so it's very common. Sometimes people will use for oxalate because it can kind of bind in multiple places. We'll also use like the bis, the tris. For us, you could go either way with oxalate. You could just use di or tri if you like. But sometimes people will use bis or tris with oxalate as well. But definitely that ethyl endyl diamine, because it does have that prefix in there, is very commonly used. Now, in addition to that, the oxidation number of the metal is typically written in Roman numerals, and that's not a big difference because typically our transition metals, we usually do use Roman numerals. Um, One of the few differences are, though, that you do come across in these sort of coordination compounds is transition metals like zinc, cadmium, and silver, which does have a fixed charge. We will still, in this case, use Roman numerals for those guys. So usually we don't use Roman numerals for zinc, cadmium, or silver, but in this sort of naming, they still use it. Also, a really odd thing that sometimes does occur in this type of naming is you'll get a neutral metal that has no charge. So people use parentheses and put 0 in as well. So it is possible, as odd as this might sound, to end up with a metal with a neutral charge. And we do, not really Roman numeral, but kind of parentheses, and 0 is sometimes used in lieu of the Roman numerals. So it's kind of a weird thing that could kind of happen with these coordination compounds. Now, the other thing that's also kind of different is this, and it has to do with the way that we name the metal that's in the complex ion part. So if your complex ion is a positive complex ion, so just as we just saw, we could have a complex ion that's negative or one that's positive. If your complex ion is positive, then you just use the regular old name like we normally think about, like iron or nickel or whatever it may be. If your complex ion is negative, then we kind of roll with sort of the older school type names for the metals, and those are the guys that typically end with 8. So instead of iron, it would be ferrate. Instead of copper, it would be cuprate, plumate, and so forth. So we kind of roll with chromate. We kind of roll with the older school names for those metals when the negative guy is when the complex ion is negative. Any questions on that there? So let's take a look at some of these sort of ligands and some of the names that we sometimes come across. For example, here again, water's aqua or aqua, amine, methylamine, carbonyl. The halogens are sort of named like they do in organic, fluoro, chloral, bromo, iodo. Hydroxo for hydroxides, cyano there for cyanide, are the names of the ligands. Here again is some of the metal names, as I was just talking about. It's kind of the older school names, and these would be the names, again, that you would use if your complex ion is negative for the metal part that's in your complex ion. So iron would be ferrate, cuprate, plumate, argentate, arurate, stannate are some of these guys here. Here's a few more, carbonate is carbonato, and oxalate is oxalato. I feel like I'm ordering a drink, a little carbonato oxalato with a topper of some bromo or something. This is ethylenediamine. Again, in the naming, most people will roll still with the kind of little abbreviation for it. This is actually EDTA here, ethylenediamine tetraaceto. So some of these guys have some interesting sort of names that come about it. So let's take a look at those guys that we just did here. So why don't you take a moment and see what you come up with for each of these guys if you had to name them. So why don't you give it a try? Actually, here, we'll do this first guy together just to see how it goes. So we'll do this guy together. So starting with this guy here, we're going to start with our counter ion. And the good thing about the counter ions are they're pretty much just named like normal. So you just use the name of it. So if it is a metal that comes first, you just use the name of the metal. If it's a polyatomic ion or something like that, you would just use the name of the polyatomic ion. If it's sort of a negative ion, you would use IDE like normal. So the counter ions are pretty much named like normal. So this would be potassium. And it doesn't really matter how many of those counter ions you would have. For example, if we had K2O, we would call that potassium oxide. So it's the same idea. It doesn't really matter, how many you have. Now, when we get to our complex ion part, we've already sort of dissected this, and we already see that our complex ion part is negative, which means that we do want to use the older name for gold. So again, we would roll to our table, or when we know our table, right? Whatever it is here, and we would want to use arurate instead of gold here, again, because the complex ion part is negative. So we already also figured out the oxidation state on this guy. So we know we have a arurate Roman numeral 3 for the oxidation state that is on it. We have 4, and the prefix for 4 is tetra. And hydroxide, again, doesn't go by hydroxide here. It does go by hydroxo, as we saw right here. Hydroxo. So we would use hydroxo here, and that would be tetrahydroxo. So putting this together in terms of the complex ion part, we will go with our ligands first. So this would be tetrahydroxo, and our metal should come at the end, arurate 3. So this is potassium tetrahydroxo, arurate 3 in this case. Any questions on that name there? All right, so why don't you name this one here? See what you come up with. Okay, so let's take a look. So once again, we sort of dissected this guy a little bit earlier. We know our complex ion part comes first. And because of that, we know we could also just use the regular name for our metal. We don't have to use the kind of older school name. So we do know that at the end of the complex ion part, we should have a chromium. And we also figured out the oxidation state earlier, Roman numeral 3, because of the charge on it. We do have 6 of the ammonia ligands, and 6 is hexa and amine. And that's really the complex ion part of the name. And that's what we would start with, which is our ligands. So this would be hexamine, chromium, Roman numeral 3. And once again, here we come to our counter ion, which we just use the name of it. And this would be nitrate in this case. Any questions on that name there? Now, what would be the name if perhaps I did not have the counter ions present? So if I did wanted to say name these guys without the counter ions present, So as I say, we didn't have this, we just had the ion, we would get rid of the potassium. And this would pretty much be the same name, except at the end, we just put ion at the end of it, yeah. And same thing here, if we just had the complex ion part and not the counter ion part there. And in this case, it was a +3. We would also obviously not use the counter ion name, and we would just put ion at the end of it. So we do use the same rules to name the complex ion by itself without the counter ion present. And again, we would just have ion sort of put at the end of it. Any question on that one there? By the way, coordination number on the first one is? Coordination number on this one is? It is 4. Yeah, those are each hydroxide. They're each attached monodentates, right? So that'll give us 4. Coordination number on this guy here is 6 in this case. Again, each of the ammonias will attach to the nitrogen. Gives you basically 1 attachment per ammonia. And you got 6 of them. Will give you a coordination number of 6 in this case. Yeah. Any questions on that there? All right, let's have some fun with naming here, maybe. Let's see. All right, why don't you try this one and see what you come up with? Okay, so let's take a look at it. We got here, if we just look at it, our counter ion is going to come first. And we know here our complex ion here is going to come second. So really just from that placement, we know this is sort of the charges that we should have on each of those guys. We may want to sort of figure out some oxidation states here. So we'll start here with oxygen -2. And there's 3 of them, which gives you a -6. The potassium is +1, and there's 3 of them, gives you a +3. So in this case here, the chromium is going to be +3 to balance it out to 0. In terms of the name, we could start with just the counter ion, which would be potassium. Once again, it doesn't matter really how many you have of them. It's just going to be called potassium. Now, because our complex ion is negative here, we do have to go with chromate, sort of the older school name rather than chromium in this case because of the negative ion. And that is what we see here when we just pull out the complex ion part of it. It has a -3 charge from the -6 and +3 happening here. And that once again is why we do have 3 of the potassiums to act as a counter ion in this case to balances out that -3 charge. So we do have, we do need a Roman numeral, which would be 3 for our chromate. We also have oxalate, which again is not called oxalate anymore. It is called the oxalato there. And that is what we want to call it. And we do have 3 of them, which would be like a trioxalato. This again, as I mentioned, is a one that sometimes people will use the tris with, oxalato. So for us, we could go either way on this, just so you know. You will sometimes see tris used with it. That I think is everything that we need sort of to name it. We're going to go with our ligands first. So we'll go trioxalato. And again, this would be chromate Roman numeral 3 in this particular case. Again, some people may call it potassium tris oxalato chromate 3 as well. Any question on that one there? By the way, I think maybe on the notes, it was actually a hydrate, believe it or not. So you can incorporate other type of naming that maybe you've seen before, like this. When you have a little dot and waters after it, right, that makes it a hydrate. And you just name hydrates based on how many waters there are. So if you were going to have this guy, this would be potassium trioxalato chromate 3 trihydrate. Tri for 3 waters, hydrate for water. So I could also do like a hydrate situation that happens as well. Any question on that? By the way, the coordination number in this case is? Coordination number in this case is 6, as the oxalate is a bidentate. So in this case, basically what we have is a chromium that has 1 oxalate, 1 and 2, 2 oxalates, and I'll just draw one more this way, maybe. And 1 and 2, right? So again, here we have 1, 2, 3, 4, 5, and 6. Again, each one combined in twice, giving us a coordination number here of 6. And again, as I mentioned before, not always the coefficient or the subscript that you see down there on the bottom. Any questions on that one there? All right, so why don't you give the name for the first one and give the formula for the next one. Here's some more. Okay, so let's take a look here at the first one. Once again, just by the way the formula is written, we see those brackets, so that tells us our complex ion here is coming first, and our counter ion is coming second. That automatically tells us that our complex ion is positive, our counter ion is negative. So that allows us to know that we could just use the regular name there for the metal. We do want to figure out the oxidation state on the metal and the complex ion. Water is 0, it has no charge. Each of these CLs is -1. There's 2 of them, gives you a -2. We also have a CL on the outside, which is -1. So that altogether is -3. That means that the chromium here will be rolling with a +3 charge. So we know that we have a chromium Roman numeral 3 happening. We also have 4 waters. So the prefix for 4 is tetra, and you could go aqua, whichever way you would like to roll with that. We also have 2 of the CLs, and 2 is di, and that is chloral. So that is all the sort of complex ion part of the name. Again, we're going to go with ligands first in alphabetical order. In this case, which one should come first? It is actually this guy, because we're going to ignore the prefixes and look at the actual ligand names. So this is going to be tetra, aquo, dichloral, chromium, as the metal should come at the end of the complex ion name, which is what this part of it is. And then our counter ion here is also a Cl. And again, we just name it like a normal Cl minus, which would be chloride. So this would be tetraaquo dichloral chromium 3 chloride. Any questions on that one there? Again, if we look at just the complex ion part, we got this and this. And once again, that is +3, that is 0, that is -2. That is a +1 overall charge for our complex ion. That is why when we look at the counter ion, we just have a chloride there to balance it out. Coordination number here for this guy would be 6. It has 4 waters, which are monodentate, and 2 CLs attached to it. So again, the metal doesn't have to have all the same ligands attached. In this case, got a couple different ligands basically attached in this case. Any questions on that there? All right, so look at the bottom one here. We actually want to write the formula here, and we could just really think about the parts. I do know, by the way, when I look at this, that this is my complex ion part. And I know that for two reasons. One, it comes here with the metal at the end of it, so that has to be the complex ion part. And our sulfate here will be our counter ion in this particular case. I also know that it is positive because it comes first, because I could also see it's just a regular cobalt name for it, not, cobaltates or anything like that. So we're just going to take the part. So tris is 3. Ethylendyl is that En. And like I said before, very common. You can just use the abbreviation if you like. Otherwise, you can also obviously write the formula in there if you like, which is this guy. And I would say most people roll with sort of the En part of it, but again, you can do it that way as well. Cobalt, Roman numeral 2 there means I do have a cobalt with a +2 charge. That means when I put it together in terms of my complex ion parts, metal, and then my ligand here. Now, if I just look at the complex ion part, this En is neutral. The cobalt is +2, which means overall, my complex ion has a +2 charge. And that's really important because we need to figure out how many of our counter ions we need. And in this case, my counter ion is sulfate, which has a -2 charge. So because it's +2, I will just need really one sulfate to balance that out. And that would get me my coordination compound that looks something like this with my one sulfate to balance it out. Any questions on that formula there? All right, let's try a couple more here. By the way, coordination number on the bottom guy is? Coordination on the bottom guy is 6. Yes. Once again, this is bidentate, so you get a 2-for-1 in the bonding area here. Yeah. All right, so let's try maybe these here. So I give the name for each of the following here. See what you come up with. So we'll start the first one. Once again, we do see our complex ion coming first. So again, that tells us that's positive. That means the Cl here would be our counter ion, which would be negative in this case. Looking at the oxidation state on our cobalt here, we have 0 for our ammonia. We do have -1 for the chloride. That's part of the complex ion. We do have really like a -2 happening there on the outside. And that again here will make our cobalt be pretty much Roman numeral 3 and a +3 oxidation state. We do have cobalt, Roman numeral 3. We could use the regular name of the metal because our complex ion in this case is positive. We do have 5, which is pentamine for our ammonias. And we do have 1 chlorine or chloride, which is a chloral. Again, we're going to go alphabetical here, ignoring prefixes. So A before C. And we will start with our pentamine, chloral. Again, the metal coming at the end of the complex ion name. Cobalt, Roman numeral 3. And here we will name our counter ion like normal. And again, doesn't matter how many you have of them. That would be a little chloride action happening there. Yeah. Any questions on that name there? Coordination number on this one is going to be 6 as well, as we have 5 ammonias here, which are monodentate, and 1 chloride, which is monodentate. So that is 6 attached directly to our cobalt. And again, if we just looked at the complex ion part of it, with a +3 there and a -1, that's going to be a +2 charge, which again is why we need 2 of the chlorides there to balance out the charge. If we were just naming the complex ion part of this guy, it would be pentamine chloral cobalt 3 ion would be the name of it. Any questions on any part of that there? Looking at the one on the bottom there, we got our complex ion that's actually coming second here. So that means it's going to be negative. Our potassium will be our counter ion, which would then be positive. So with that being negative, that does tell us we do need to use the old school name here. And we do want to figure out some oxidation states. So Cn is Cn minus, and there's -1. There's 6 of them. Gives us a -6 for that part of it. That is +1 for the potassium. There's 3 of them. Gives us a +3. So +3 and -6 means that the iron here is going to be +3 in this particular case. That means we do need to go with the ferrate 3 as the complex ion is negative. We also have hexacyano for our 6 cyanides. So we'll start here actually with our counter ion, and we're just going to use the name, which is potassium. We will go with our ligands first, which will be hexacyano, and our metal at the end of the name here, ferrate, Roman numeral 3. Any questions on that one there? Coordination number on this one also going to be a 6. And if we just look at the complex ion part, we are looking at a -3 charge, which is why, again, we have the 3 +1 potassiums to counter it out. Any questions on that there? All right, then let's do some formulas for these guys here. So write the proper formulas for each of these guys, see what you come up with. Okay, so let's take a look. We'll do first one here, and this is my complex ion part because remember, again, the metal will always come at the end of that part of the name, and that's where we do see the metal with the Roman numerals. So I do know that's my complex ion. That would be my counter ion in this case. We also know it's positive as it comes first. So just taking out the parts, triamine, that is basically ammonia, and tri is 3, so we got 3 of those. That takes care of that part of it. Bromo is Br minus, and platinum is Pt with a +2 charge. So we do just need to put these guys together here for our complex ion part. And we'll have Pt NH3 3Br. We could also sort of figure out the overall charge on our complex ion. We know this guy's +2, 0, and -1. That is going to give us basically a +1 charge on our complex ion. And that's important because that allows us to really know how many of these counter ions that we need, since each of them are -1 in this case. So putting those guys together should give us a coordination compound that looks something like this. In this particular case, coordination number in this case would be 4. 3 ammonias and 1 bromine basically attached to the platinum in the middle. Any question on that one there? Coming here to the next one, we actually see the metal on the second part of the name, which means that that is our complex ion. We also now know it's negative as well because we do see kind of the older school name. This guy would be our counter ion. So potassium, which is our counter ion, is really just K+. Hexafluoral is 6 fluorines. Cobaltate is cobalt with a +3 charge. So starting with our complex ion part, we have a cobalt and 6 of those guys. That's going to give us here a -6 and a +3. Give us a -3 overall charge for our complex ion. That means that we do need not 1, not 2, but we do need 3 of these counter ions to balance it out. So putting that together, K3CO, you could actually just do F6 without the parentheses if you want. look something like that. Any question on that one there? Coordination number on this guy would be 6 in this case. All 6 of the fluorines are basically attached to the cobalt in the complex ion part. Any question on how to name these guys, how to write the formulas, coordination numbers, oxidation states? You need to be able to do all that, so I imagine. Yes. Any questions on any of that? Okay. All right, so I think we'll lay it up for now here.